So last time I introduced the notion of an enriched category. So we had a V category, or a category enriched in some monoidal category. V was supposed to be a set, the objects of the category, of the enriched category, and for each pair of elements we were supposed to have an element in the enriched category, which was supposed to be our HOMs from A to B for the objects A and B. So, and then what I did was I gave you an idea of the monoidal category we want to enrich over, which is this R plus, in order to get metric spaces, I should say. So let me just remind you about R plus. So R plus is the objects of R plus. So this is just the non-negative real numbers with infinity stuck on at the end, and this is sort of considered as a category in the sort of terms of a poset. So we've got precisely one morphism from an object from a number A to a number B when A is bigger than or equal to B. Okay, and with no morphism otherwise. So they're the morphisms, and the composition is determined for you. And the monoidal structure we put on this category is just the usual additive additive sum in the arithmetic sense, so just the sum of numbers. And 0 will be the unit object for this monoidal structure. Okay, so what we want to do is look at what a category enriched in this is. Now suppose we have such a thing, so this is going to be, C is going to be an R plus category, or a category enriched in R plus. So we've got a set, an underlying set, and for all elements in this set we've got this HOM is supposed to be an object in B. But, well, the object we know, so this is just supposed to be something, some number from 0 to infinity. So straight away that's slightly strange. We've not got a set of morphisms from A to B, so we've got some set here. Suppose we have A and B. So normally in a category we would have, between A and B, we'd have a whole wodge of stuff here. We'd have a set of morphisms going from A to B. Here we don't have a set, we just have a number. So that's slightly strange because this isn't a concrete category, so it doesn't, each object isn't itself a set. Okay. So then we need composition. So for all triples in the set, objects of C, we need a morphism from HOM, tensor HOM to HOM. So tensor we just know is plus. So these are all elements of R plus, so these are all numbers. The HOMs are all numbers. So there exists a morphism from something to something else inside R plus. So to say there exists a morphism, remember, is precisely to say that the thing on the left is bigger than or equal to the thing on the right. So there exists a morphism is exactly the same as saying that is bigger than or equal to that. So instantly you sort of see the triangle inequality cropping up, and there exists a morphism. So our unit object is just 0, and if we have a morphism from 0 to something else, this is just saying that 0 is bigger than or equal to HOM AA. So that's a slightly strange way of writing it. We know that HOM AA is always in 0 infinity. So that's the same as saying that that equals 0. But this is just the way that it crops up in this situation. So the associativity and unit constraints are actually vacuous in this. Vacuous? I don't want to put too many U's in there. So they're actually vacuous in this instance. Right, so what we get is something that looks kind of like a metric space. We've got a set, and assigning a number to each pair of points satisfying the triangle equality, and such that the distance from A to A, from any point to itself, is always 0. So this isn't quite a metric space. So this is called such a thing is called a generalized metric space. So this is in the sense generalized metric space in the sense of Lovere. So in what sense is it more general than a metric space? So there's three senses. So it's not symmetric. So in general we don't have DAB in general. We don't have DAB is equal to DBA. That's not required anywhere. So is that reasonable? Well, often you get things which appear like metric spaces but don't have this symmetry condition. The example Lovere gives is if we have maybe a collection of villages in the Alps and the distance between two villages is so that the time it takes you to get from one to the other. Now this could be a very hilly region, and it's not always the case that going from one village to another takes you the same amount of time as going back along your journey. Going uphill is often slower than coming back down. So that would be an example. Another example is maybe the cost of travelling between two places. So to get from England to Wales, if you're going along the road bridge, then that'll cost you, I don't know what it is, £4 maybe. Going from Wales to England costs you nothing. So you've got some asymmetry, but you could look at the cost metric, which isn't going to be a metric in the traditional sense, but it is going to be one of these generalized metrics. And so it's not symmetric. You might have DAB equals 0 with A not equal to B. So that can happen. So as I say, sometimes the cost of going from one place to the other might be 0, even though they're different places, and we allow the infinite distance. So that's occasionally useful if it's absolutely impossible to get from one place to another. Okay, so that means that every metric space is an example of one of these generalized metric spaces. So we can consider metric spaces or metric space theory as a subset of enriched category theory, if you like. And that's quite useful. I mean, well, it's because you get to see that many notions in say, metric space theory are just sort of the appropriate notions categorically. Let's just have a quick look at the idea of a V-functor. So suppose we've got we've got two V categories. So these are V categories. Some monoidal category V. So what is a V-functor? So phi consists of, firstly, we have a map, so just of sets. So from C, the objects of C to the objects of D, each object of C gets sent to a object of D. So this is just a set map. And for all A and B in C, we get a morphism, which of course is also called phi. So we've got hom AB to hom phi A phi B. So this is a morphism in V. And this has to satisfy, well, you can guess pretty much what this is going to have to satisfy because you know what a functor satisfies. So this has to commute with composition. So I'll just let you figure out what that means. But if we just look at the example, so if we take V is R plus, then this is just saying that we must have hom of AB is bigger than or equal to hom of phi A phi B. So in the generalized metric space setting, an appropriate notion of a morphism between two generalized metric spaces is just a set map which is non-expanding. It just doesn't increase the distance between 2 points. So these are sometimes called metric maps. So I'll leave that there.